welcome everybody. It's my pleasure to announce that today's seminar will be a presentation by Ms. Katarzyna Smelcerz, who's preparing her PhD thesis around the detectors of cosmic rays, something like that. So I don't have much to speak about it, so let's take the floor. Let's give the floor to Katarzyna.
Thank you.
Please.
Thank you. Hello and welcome, everybody. My name is Katarzyna Smelcerz. We know each other from work, most of us. If there is anyone I don't know remotely, hello and welcome once again. What I want to present today is a topic, distributed and mobile scintillator-based detector system for cosmic ray and background radiation monitoring. It's my PhD has title, and it's held in the Nuclear Institute of Physics Science of Polish Academy of Science, and my advisor is Professor Jetelski. So I will come to the basics, and I will start with a definition. What is radiation, and what does it mean that something is radiated? So as in the book Radiation Detection and Measurement, one of the basics of the book, it says that radiation is the emission and propagation of energy through space or matter from waves or particles. And what we don't really realize quite often is that every day around us, there is radiation. We live with it, and it's so-called background radiation. So as some research found, the radiation, background radiation, is quite significant within the materials around us, such as buildings. For example, as we can see, it's cement, gypsum, gravel, and brick. And even in the food, we can find nowadays the radiated particles in beef, halibut, so we know some oysters, etc. So this is one of the sources of radiation around us. What is more? For sure, cosmic radiation. And this is the radiation that is coming from space to Earth. And I will speak about it a bit more in 1 minute. And of course, we also have radiation from gas in the air. Hello. So what we can say when we want to build a mobile detector system, for sure, we have to be aware of this, that the thing we will detect here on Earth will consist of cosmic radiation and for sure of the background radiation. And it's important to remember about it because the background radiation is very difficult to subtract from any detection we will get in our equipment. Okay. So now let's take a look a bit more closely at the cosmic radiation, and one of the particles that is quite well measured, it's neutron. So what we can see when we measure neutron dose is that the higher magnetic latitude it is, the bigger dose we get. And the difference between sea level and the height above the sea level is quite big because it's 3 times more. This plot you see here, where you have the curve with sea level, it's multiplied by 300, so it can be placed in one plot. And why do we talk about it? Because it has got a quite big influence also on our health. So, for example, when there's the aviation norms for aircrew or for people who work in aviation, they calculate how much time pilots and crew are spending up in the air, because the dose of this radiation is much bigger than the dose on the sea level. Okay, so with remembering of that, we can ask ourselves, okay, so where from are the neutrons are coming? So the neutrons are basically produced as secondary particles from the primary particle that interacts with our atmosphere. And what we see, we have a formation of so-called air showers. So there's the whole scheme for that. How the extensive air showers are produced. We have the primary particle, for example, proton. It hits the particle of atmosphere, and what we get three main cascades: ionic components, hadronic, and electromagnetic. In hadronic, we get proton, neutron, pion, and kaon. From ionic components, we get muons. And from electromagnetic components, we get electron, positron, and photon. And the reason why I'm saying about it is just to have a background, because I will tell in a minute about this, what the system is measuring exactly. Because at the beginning, like I said, one of the sources we will measure is the background radiation. But except the background radiation, there's also this type of radiation, the cosmic ray. So my system was designed to measure and to detect muons, because astrophysicists, they really like to research on muons. They can tell us a lot about hadronic models. They can tell also a lot about high energy interactions, and they are used for something that is called muonography, which is a way of imagining, detecting objects that are high and are not well seen for human eyes. I will speak about it in a minute. So just to summarize the muons, as we see, they are produced from charge mesons, mainly pions, and they are dominant component on our ground level. The typical flux from statistics says that 1 muon comes every minute per 1 square centimeter. And with muons, we have to also remember that they have very high energies and they are highly penetrating particles. What it means, once again, when we're making the experiment in laboratory, even if we hide behind the high density material, our detector, in a special chamber, the muon always will come through this material, and there is a chance that our system will detect that. Okay. What we have to also remember is this, that the lifetime of this particle is very short. These are microseconds. So, of course, the reason why we can detect it on Earth and why we say that they are so highly penetrating, they even come from mountains or buildings everywhere, is because of the time dilatation. They travel very fast, so we can measure them on Earth. And the known systems that we can see in laboratories that detect muons are very often very professional detectors, which are very expensive and also very difficult to build. I did a scholarship from European International Atomic Agency, and I spent months in Paris in Saclay. They have an institute that is building such detectors for monography and for to detect other particles. So I had a chance to see how other teams are building the really professional equipment, and it's really impressive. But one thing we have to remember is that many scientists are complaining that the equipment is very expensive and very difficult to get. So the idea of producing something cheaper, but maybe with not such a good resolution, is also very interesting for the field and for other scientists I was talking with. So, if I wanted to divide the detectors into main groups, I would say that we have scintillation detectors, and this is the type of the detector I'm constructing. We have also gases detectors, and this is the detector I was working on when I was there on the scholarship, and other detectors, tracking detectors, which consist of nuclear emulsion. And honestly, this third one I have never been working yet with, so I don't have this engineering experience with the third group. Mm-hmm. Okay, and so I told already a bit about motivation of my work. Like I said, the solutions that are right now are large and expensive, also very difficult to build. They are also, because of their size, they are stationary, so we cannot move them. And of course, because of those 2 points, they are limited. They have limited accessibility. So, is it possible to build something within PhD hands? Well, yes, I believe it is. What we need is, of course, a lot of patience, because not first prototype will ever work. And we also need a help of other team. And this is a really big thank you also for the lab of my supervisor. This material you see here right now here, it's called scintillator. And this is the basic material for scintillator detectors. Think very clearly, it's just a piece of plastic, but this plastic consists of fluorescent material, which provides photon deposition in material if high energy particle hits the material. So we have some material that will give us photon if high energy particle comes through this material. Perfect. What else we need? We need to catch those photons, detect the number or the amplitude of the event. And this is some very, very small chip. Right now, I'm not sure if it's well seen on the picture, but basically it's right here. It's called SIMP, or SIMP, and it's a silicon photomultiplier diode. And the whole idea of constructing such a detector looks less or more like this. I take a piece of this plastic, and because I have such small SIMP, it's only 6 per 6 millimeters, I need to amplify the chances of catching the photon. So I flip it around the special foil that is reflecting the photons, and I leave only a small piece empty in the middle, so any photon that comes out from this material will enter to the SIMP, the photomultiplier. Okay, so that's the idea. but also we have to remember about this, that around us there is always a light pollution. Even in the evening there is the light. So what we do, we also have to cover this architecture into something that is light-proof and will not let the photons from outside to enter. Okay, so that's the basic. But what next? I wanted the detector to be mobile, so I developed this is one of the versions of the prototype. This one is with battery. Right now, the current version is supplied by power bank. Of course, it could be also supplied by USB cable. If we leave it next to the computer, that's also fine. And we wanted it to be quite small because of 2 reasons. First reason is this, that it would be cheaper, because what is quite expensive to be produced is this plastic scintillator. Not many people know how to do it, and it's really the knowledge how to. And another thing is this, that it's just more portable. So in this version, I just wanted to point out that if you take a look, the housing is prepared exactly for the size of the scintillator, which later turned out it's not the best idea, and I will tell it about it in a second. Okay, so another version of the prototype is the current version, that is the final, I hope, and I have it with me today. You can see it on the pictures. It has changed a bit. So we have here pictures from 3 experiments. First one is my detector with 1 scintillator only. There is a different scintillator, because this one is not the plastic one, this one is a cesium scintillator, because different scintillators are sensitive for different types of particles. And here I have a radiation source, it's the cesium. And I was doing the calibration of my measurements. So I was watching the data I was getting from ADC and the shape of the signal, as well as the noise of the ADC. Second picture presents another experiment setup. It's for detecting the muons. Because maybe I can remember, I said at the beginning, muons, they have very short lifetime. So what it means, like, we have some time on Earth to, of course, observe them, but the only way to discriminate muons from the background radiation is to do something what is called coincidence. And the coincidence tells us that the event had place as well, like in the top level, like in the bottom level, within the coincidence time window. So, of course, many people will tell the shortest window, the better resolution. And in some ways, yes. However, the experiment we were also providing with my supervisor in his lab, with even professional muon detectors, they showed that sometimes relaxing the time window between the coincidence give us better results because the electronic of the gate of the 2 levels is not always very well synchronized, and sometimes we're missing something. However, in my case, in my detector, it's 2.5 nanoseconds. And what I have here only 1 gate. It's AND gate. So I'm checking if the event within 2.5 nanoseconds had place on the top and on the bottom level. If yes, I classified it as muons. As a muon, I'm sorry, as a muon, one particle, not many. And the third setup, it's muon telescope. So it's what we wanted to show is that the system could be used as a telescope if we had better funding. What I mean, if we were able to produce smaller scintillators, so one scintillator per one SIM signal, so photomultiplier, and this would be 6 millimeters per 6 millimeters, and this would be tape as 1 pixel. However, right now we don't have any more funding, so I have one SIMP. They are quite expensive components. But what we could do with this telescope, I printed parts of the 3D printer part I bought from the mechanical company. This modules we can move on this tube, so they can be closer or they can be farther. And one thing also with this experiment, another one, is to prove that what I detect are really muons. Because if we have one detector right here and one right here, they are 5 per 5 centimeters. And muons mainly are coming straight from Earth, mainly. Not all, but about 90% of them. So let's say with small angle they are coming like this. Okay, we can see that if I push farther another detector, I will get less events because one muon that could still be detected by the module number 1 will miss the module number 2. So it's very easy experiment to prove that what I'm detecting are really muons, because the number of detected muons is decreasing with the bigger distance I make between the stations. Okay, yes. And I already told a bit about the setup, but once again to summarize, what I call the station is the whole system with 2 modules. One module up, one module downstairs. And what it means, this is the setup for coincidence, so for checking the muons. If I had only one scintillator, it's the setup for measuring the background radiation or for the source radiation. Anything, because I don't need to check the coincidence right now, and it's enough. What else does this device have? The timestamp resolution is 1 millisecond. And I'm saying about timestamp, I'm adding from the hardware to each event. Coincidence window is 2.9 nanoseconds, like I said. ADC resolution is 12 bits. What else? The stations where this one is designed with 2.4 gigahertz wireless communication. Previous versions, they had 169 megahertz radio communication. But in the end, we decided this higher frequency, of course, with some costs. I will tell about it in a minute. It was just the system or end user requirements, let's call it this way. Okay, so what is more here? Of course, we have the scintillator, like I said, SIMP, so photomultiplier, that also detects our muon. What else? What's next? Okay, so I have a threshold, and this threshold I measured by observing the signal on oscilloscope, as well as making several experiments. Right now, the threshold is about 0.8 millivolts. It was tested with different one. So the problem is always this, that ADC gives us the noise. So if the threshold is too low, I get the data as the noise, or the other way, I get the noise as the data, classified as the data. If the threshold is too high, I miss some events, some those small small deposition of energy. Because in the end, we don't know if the particle was high energy or not. We just see the deposition of energy in the sensitive detector. Okay, if there is a coincidence setup, I check if the coincidence had place, like I said, so if the event was detected on 2 levels. If not, if there is no coincidence, I take any event that is above the threshold and is serviced by the interrupt system in my microcontroller as my event. I have a GPS that could be used for localization of the detector because it's mobile, as well as for the time, I missed the word, synchronization, excuse me. Okay, and all these things are served by STM32 microcontroller. So basically, this detection system is set up on STM microcontroller. What else I have there? I have their additional microcontroller, which is SP32, only for the communication with internet if it's needed, and as well as for the doing the registry into the SD card. So why is it into separated unit? Because I want to take as many events as possible, and the only way to do it is to not occupy the STM, ERQ, or NFIC system with other tasks. I have there a buffer, so I'm leaving the event in the buffer, and I send the data within the buffer to SP32. And SP32 has got plenty of time to do proper things with the data because it doesn't need to measure the event. There is other also quite 2 more interesting things about the system that the SP32 provides. I will tell in a second, but firstly, I wanted to tell a bit about it, how we proved that it's working, because unfortunately, sometimes it's not very easy to convince people that everything is fine. Plus, of course, it's a research, so we have to do, and it's good that we have to provide a couple of experiments. We always can find something new. Plus, it's very good for the evaluation of the system. If there are any problems, we will find that. First experiment was in a balloon. So I was supervising students' scientific club, and we had a balloon. We put the station into the balloon up into atmosphere. It was going, I think, up to, I don't remember how many kilometers. We will check on the next slide because I really forgot. I'm sorry. However, if you remember at the beginning of the slides, I said that with this, the higher we are, the bigger cosmic radiation we have. There are more high energy particles that can influence on our body. It's the same. That's why it's important for the airplane crews. And it's the same thing that we can observe during this balloon experiment. So basically, the higher the balloon was going, as we can see, the higher amplitude of the events was detected with the station. I also made a background spectrum from this experiment, and what we noticed this background spectrum is exactly how the background spectrum looks like in our world. The high energy tail, like this, not many events, but some events we can see here, especially in the logarithmic scale. We always classify them as muons, even though when we don't have a coincidence system like it was in the balloon, because it was only the background. It was only the background setup. We always decide that whatever is at the end, we say it's a muon, because it had to be very or extremely energetical particle to produce such big voltage. Okay. What also we can observe in this experiment results, that number of events with time of observation. And we also can see that the rate on the specific altitude is the highest. So once again, it's exactly what the experiment of finding the muons proves, that the higher I am in the altitude, the more energetical particles I will detect. So it was first step for me to check if the background is measured well. We decided with my supervisor that the data are satisfying, and we went to another scenario. So we wanted to check if this station is capable of creating a spectrum of the radiation source. This is the cesium, and it's quite weak and old source, so I can work with it because I don't work with very high energetical sources. However, even for this source, we got very good spectrum, which once again tells us that this system works properly. We can see here, this darker part is the background, the lighter one is the spectrum of the cesium. Once again, at the end, we have this peak, and we believe these are muons. Basically, the whole experiment was taken not on the desk, because of course it's a radiated source. It was just for a minute. I wanted to measure something with oscilloscope. It's the only way to do it, unfortunately. But for the rest of the time, these experiments are provided in the special chamber. And even in those special chambers that they don't let the radiation outside to the room where we sit or where we work, you can see that muons are coming through this material, and even they are entering the base. Okay. What next? We made also an experiment of the stability of the system. So there was a quite long measurement, 26 hours versus 2.5 hours. What we noticed, the percentage of muons in both experiments is the same. It was about 10%, and the overall stability of the system is also same or very similar. So what we see right now from these slides that were provided, we can see that the system is able to detect muons. The system has got also quite good stability. The system can create a spectrum of source radiation. What is more, the system also can detect the source radiation, because we are sensitive for the number of events. And when we have the radiated source, the number of events, of course, grows. Final step was creating a simulation in GÉANT for which is favorite software for each business. These simulations, as you can see, we have very similar spectrum to those my system has created or detected in the background. This is the neon spectrum. And this is the one of the things I know because of this situation here, that some neons, unfortunately, we are not able to detect. We have about 10% of the all events are neons, while during the simulation, it's about 30%. So the reasons are few. First of all, it's not FPGA, but it's microcontroller. So the time resolution and the whole interrupt system takes a bit too much time to have such a good resolution. However, even with very professional detector systems, it's also never 30%. It's 15, 20, but not 30 exactly. And the setup that I created in Giant is presented on the right corner. It was two scintillators with SNILP attached to them, and also with foil, reflective oil foil, and this black matter that prevents us from the outside light. It's just not seen on the picture, so it could be clearer. Okay, so what we can see also about our coincidence, it's that thing I already said, so maybe I will not repeat it. Basically, I'm able to detect neons. The bigger distance between detectors, the less neon I get, and the overall efficiency is the overall neon detection is 10% in experiment setup. What else the station was provided with? Because the scientists they wanted to have mobile detectors. So if you want mobile, I asked them, how will you collect the data? And the answer was, okay, maybe we will go for a walk. Or I said, maybe you will get it to your room with the wireless communication. So we started to talking about it, and so they said, okay, so if it's this way, so let's create a scenario where we don't have internet everywhere, and maybe it's a desert or maybe it's a forest. So in this way, that's why this station was created. It was presented on the conference in Wisconsin-Madison, and this station provided quite really good range, because we were able to, we got 1.5 kilometers in urban area of the distance. However, it's the communication is very slow. So at the beginning, we didn't know how many events we will have, how often we will have to send them. And in the end, we decided it's too slow. So we moved to 2.4 gigahertz. I'm sorry, I don't know why it's mistake. Okay, it's a mistake here. I will correct it later. Excuse me. It's 2.4 gigahertz. Packet loss is much smaller in this case. However, the range is also much smaller because it's about 40 meters only in urban area. Comparing to 1.5 kilometers, it's a big difference. However, that was the decision at the end, and I perfectly understand it because in the end we have much more events than we thought at the beginning we would be able to detect. So this is this old communication system, and okay, we can ask ourselves, why was it even created? So a bit of backstory for that. I started to working in this project when there was no detector yet created. There was no detectors, and my goal, my contract was to create a wireless long-range communication system. So it was a bit backward developed. First we had the radio station. Later they asked me to create the detector as well for that. Okay, so overall system architecture, how we can describe. Right now, we have detectors, which are connected wireless, or also can be connected to the internet, but if not, there's the perfect 2.4 gigahertz radio connection with something what is called sync. And it's a typical star topology. Sync is the station that collects data from all the detectors, and in the end, we assume that our sync is writing down those data on another SD backup card, or what is the perfect scenario? Sync has got Wi-Fi. So this is this one station that has got access to the Wi-Fi, and these data are sent later to something what is called MQTT. It's a broker for data, and MQTT is connected to Influx database. When I have data in Influx, everything is very easy to plot and chart, and any scientist can see the data from his room or from his office. And this is basically the system I was showing during the scientific days on September. That was in our university. Okay, when I was talking about ions, I thought that they are also used for something that is called immunography. And immunography is a great tool for projecting or for creating a distribution of objects behind or in the hidden place that we don't see. With this way, one of the chamber in one of the Helps pyramid was discovered. So it's really serious thing, but unfortunately what we need is a very good resolution on the detector. Basically, it works this way that the particle, when it's coming through high density objects, it scatters. So it's never like this exactly straight line. It changed a bit the trajectory a bit. So this angle we know how to calculate, especially if we know from which material the object is created. And I had a chance to do some experiment like that when I was in Paris. I was working on gaseous detector that they had in the laboratory, and our goal was each person to put the blocks in a different position, and later to check if with muons we are able to create the map of these objects. Of course, we had to make the data acquisition. Later, we provided the POCAP algorithm. That was just exactly checking what I said, the position of the muon on two top layers and the position of the muon of two bottom layers, checking the angle that was between those two lines. And with this information, I was able to recreate the map of these blocks. So I think it's very interesting method. I really never knew about it when I was studying. I just found out it on my PhD, and I'm really amazed how it's well working. In the end, we got the box. Each of the person got different box, and there was some configuration that once again we didn't know. Only with muons, we are able to detect what is in the box and how it's placed. So this one, so when the box was standing like this, the second slide is with flipped box this way. And yes, so what I would like to, at the end, to say, it's the summary of everything I presented. So basically, the system I created is modular, is able to measure background radiation as well as any source of radiation is able to detect. We can detect neons. The operation in dynamic condition, which was binary, was also successful. What I would like to keep on working in the future, for sure, I would like to get some funding, and I would like to create a matrix for the radiography based on the signal. And of course, I'm sure there are more simulation I can do to provide also more information about the system in reality. And that's all. Thank you so much for listening my presentation today. I was very stressed. Thank you. I have this detector with me here. If anyone wants to see it, of course you can. I forgot to say about one thing, maybe if I can. At the beginning, like I showed you, it was always attached to the PCB. And, we said that, okay, because we have these small scintillators, but maybe one day we will have bigger, because we cook them in the laboratory, like in the oven. So maybe we will be successful with some bigger size. And then it's much easier when the mechanic is separated, because this part is printed on 3D printer. So I can attach it to any shape of the, adjust it to any shape of the scintillator I have. Even if it's bigger, it still will work on such small piece of PCB. So that's it. I just forgot to say thank you once again.
Thank you very much for the consistent presentations. And may I ask for questions? Let me have my question, please. You mentioned about the direction that ions come from. And my question is whether there are something equivalent to lens, to optical lens in the ionography.
To optical lens?
Yeah, because the nature of the radiation is quite similar. The energy is different, the range is different, but the nature is still electromagnetic radiation.
Yeah, okay, so basically, I'm not sure if I understand your question, but so the direction and the amount of radiation that comes to us depends on a couple of things. So on the poles, it's bigger. It's much bigger because of the electromagnetic field.
Yeah, but so you may imagine you make some lens, some devices to focus.
So yes, there are detectors like that. Of course, yes. So basically, if we want to detect the exact direction of the radiation, the detector with size of the lens, it would help because it focuses the energy inside. Yes, it's. We were even thinking about it, but it's time and some money too. But there was this idea even with my supervisor.
I imagine that first of all you want to have a very small diet, but on the other hand, you need to focus more energy on the small piece.
Yes.
That's a question of that's a background of the question. And should we have another question? If I have any question.
What was this mysterious thing hidden in the box? Because you showed us only picture created by neons, but what was...
It was exactly this. It was, there were the LED blocks put into the, like when you looked on the top, this way, the blocks were placed like this, LED blocks. Okay. But when we flipped the box, because it was a trap for us, you could see that the blocks are, it's built of different shape of the box, right? It's a second dimension. So this is the same box, but in different orientation.
Okay.
So before going further, I would like to make a surprise. So assuming that was a doctoral presentation, should we have any remark? Long, too short, too detailed?
You know, I have one thing to indicate. Descriptions on the on pictures. Sometimes there were
blurred. Yeah, I noticed it.
Like here, for example.
Okay.
Yeah.
Okay. Yes.
Something like the picture to let in.
Yeah. Or maybe each picture on each slide.
Slide.
Yeah.
So it's just that I tested it on screen on computer, so it's obviously. But you are right. Thank you. It's too small. I agree with that.
Remarks, advices. Okay, so thank you very much.
Thank you.
To me, it was excellent, really. And your device is very impressive, especially if I think about synchronization in micro nanoseconds.
Nanoseconds. Nanoseconds.